Hi guys, to pick up where we left off, a couple of examples about electric field type of stuff. These are good because they help us distinguish between two types of questions and two types of situations that we need to be familiar with. Okay, so this one is about, let's see, a charge that's placed in a field, right? So it says that there's this charge that we know its mass and it's falling in a uniform electric field. So I'm just going to draw the charge itself. There's our charge, okay? And it has a mass that we know. And let's see, well, I'm going to say that we know a distance that it falls, 5 meters. Well, we know its mass, 1 gram, which I'm going to say is 0.001 kilograms. And there's an electric field that it's in with a strength of 10,000 newtons per coulomb. It starts from rest. It hits the ground at a speed of 21 meters per second. All right, well, for sure, we know that there's a gravitational force acting on this object. All right, and since it's a charge and it's placed in an electric field, by definition, it feels a force. All right, so the question that we don't know, since we don't know the orientation of the field, we don't know if the force exerted on this charge points up or points down. But what we can do here is we can use some of this data and kinematics to figure out, ask yourself, what could I figure out knowing that stuff? Yeah, we can figure out acceleration. All right, so if we say that v squared is v naught squared plus 2a delta x, we can actually figure out what this thing's acceleration is, v squared minus v naught squared over 2 delta x. Well, if you plug in, we're going to get an acceleration of 44 meters per second squared, all right, which hopefully that identifies for you for sure the fact that there's a different force other than gravity. Well, we already know that, but it should tell us the direction of that force. Well, that force has to be downward. I'm going to draw it bigger than gravitational force because, well, gravitational force would make it accelerate at 10 meters per second squared, but it's accelerating 4.5 times that fast, so we must have a bigger force that we'll call Fe. Okay? So now what we can do is we have two forces acting on this mass. All right? So what I'm going to do is turn this into a net force statement. And we can say that Fg plus Fe equals ma. Now, why am I doing this? Because, well, we want to find, at some point, the charge on the bead. Okay? And the only place that's going to live is, well, let's see, Fg we know is mg. Well, here's the deal. We know an equation with electric field, force, and charge. All right, we said in the last video that little q refers to charges that are placed in fields and field forces. All right, so we can rewrite this as Fe equals QE. Notice, it's analogous to our Fg equals mg. M, the fundamental entity, g, the gravitational field strength. Here, charge, the fundamental entity, and electric field strength. Okay, so I'll write that as QE equals ma. All right, if we want to solve for, let's see, solve for Q, well, that's going to be QE equals ma minus mg. So we'll divide both sides by E. Right, that gets rid of our E over here. So I end up with a charge, Q, of 3.42 times 10 to the negative 6th coulombs. All right. Now, the one thing we didn't do yet is find the direction of the field. Well, if you remember, you should look back probably and look at our convention of what direction electric fields point. And by definition, they point in the direction of the force that a positive charge would feel. All right. Now, this does happen to be a positive charge. So if a positive charge is pushed downward, that means electric field that I'll draw like this. It's kind of in the way there. So these lines represent our electric field. Now, this is about what's called a uniform electric field. We're going to talk a bunch more about that a few slides from now. But the general idea is that uniform means constant. All right, so this is a field that has a constant strength and a constant direction. Okay, so a typical question there that deals with this idea of a charge that's placed in a field. Now here is a typical one where we talk about charges that make fields. Okay, and we referred to those the other day, or in the last one, as our big Q's as opposed to our little q's. Now again, we're not saying that all charges don't make fields. All charges make fields, even the charges that are quote unquote placed in a field. But you know, you can kind of think of it like, you know, well, the Earth makes a gravitational field that we can put you know, a tennis ball in, and we look at the force that acts on the tennis ball. We don't typically think about the force that acts on the Earth or the field that the tennis ball makes, but both of those things do happen. All right, in this question, we're asking about electric field strength right there. And right there is not a charge, right there is not a mass, right there is a position in space that is 2 meters from the origin. Okay, so I'm going to do a little color coding. We'll call this a blue one. We'll call this a red one. We'll call this a green one. All right, first step here is to do not really a free body diagram because it's not forces, but at least draw representations of the electric field due to each one of those charges. All right. Now, big deal is that fields point in the direction of a force that a positive charge would feel. All right. That led us in the last video to talk about the fact that fields tend to point away from positive charge and point toward negative charge. In general, if we just have point charges. These 3 charges in this question are point charges. So at this location, what I'm going to do is say the blue -4 nanocoulomb charge, it's a negative charge. So this field that I'll call E4, made by the 4 nanocoulomb charge, that charge is negative, so the field it makes points towards it. All right. Now the 5 nanocoulomb charge is positive, and I'm going to draw it, well, therefore away from that charge. And the question is bigger, smaller, or the same? Take a minute to think about that. Well, it's going to be bigger. And the reason is 2 reasons. One, we're closer to that charge, and it's a stronger charge. Okay. Now E3 is also charge 3 is also positive, but it's a weaker charge, but we're closer to it. Hard to tell here. I'm going to say, well, just arbitrarily, it looks like that. Okay? Now, if we want the net electric field, now we go to the analysis of our diagram here, and I would call it E5 plus E3 minus E4, just based on treating this like a free body diagram. We made a kind of a joke in block 1, we call it an E-body diagram, right? It's just electric fields, not forces. Okay, so how do you find each one of these? E5, E3, E4. Well, again, these are charges that make fields, right? We know the charge, and we know how far away we are from it, right? So the equation that connects electric field strength to those things is K, big Q, over R squared. Okay, so for E5, I'll use Q5 and the distance from 5. Here I'll do K, Q3 and the distance from charge 3 minus K times Q4 and the distance from R4. Don't forget to square. Now, big deal, just like we said in forces, we never ever use the sign of charge when we calculate magnitudes of forces or magnitudes of electric field strength. Right? We don't want a negative, say here, to screw up with this negative and give us something weird about our net electric field. All right, so never use sign of charge. Okay, you know, something to remember, R5, if we just want to do a little, well, R5 is that 2 meters, right, from the diagram. R3, well, it's 2 meters minus that 0.8 meters, so that's 1.2 meters. And R4, 2 meters plus that half meter, 2.5 meters. Okay? So plug in and see what you get. Well, I solved, and I get 24 newtons per coulomb to the right. How do I know to the right? Because my answer came out positive. Right? One thing I didn't say clearly, but maybe I should, and I hope we know this by now, Q refers to charge, so here's Q5, right? Here's Q3, and Q4, there's Q4. Make sure you're comfortable with the fact that that little n means nano, or 10 to the negative 9th, okay? So maybe a complicated problem, but when you break it down into reasonable steps, not too bad, okay? Now, hopefully we're comfortable with fields near point charges. All right, we need to deal with fields around typical, what I call charge distributions. All right, so to walk you through this, I went to this, I Googled electric field applet. All right, you Google electric field applet, you come up with the first hit is a Caltech site. All right, you launch it. You got to be patient. It takes a while. Notice what things on the right are checked and unchecked. All right, and what it allows you to do is place charges on the applet. Like, notice I can choose the magnitude and sign of the charge by pressing those buttons. All right, so if I choose a +4 charge arbitrarily, I put it on the applet, it draws the lines. Right? It doesn't know how to draw arrows, so it doesn't. Okay? If we reset, I draw a -2. You notice a couple of things. One, there are fewer lines. Right? We talked last time about how do you tell where a field is strong? Well, you look for where there's a lot of lines. Right? In this case, anywhere you look, there are fewer lines per unit area than there were with this stronger charge. Right? Here's an even stronger charge. Anywhere you look, more lines per unit area. All right? So the 8, whatever it is, charge, makes a stronger field than the 4, whatever it is, charge. Okay? So like I said, we want to look at some common charge distributions. And one of them is 2 like charges. Well, I guess I should do positives. I think they're both positives on this slide. So we go to this, 2 of them. Right? Now, what you notice is the field, what we call the field lines, bend away from each other. Field lines never cross. All right. Now, what we're actually seeing here, or what it's representing, is the fact that, well, the field here, hard to see maybe with that. I'll try with a red marker. The field here points like that. 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 So this is really like the addition almost. Not really addition, but you know, if you notice, hopefully the field at any location is tangent to one of those field lines. Instead of drawing a billion vectors, right, we sort of draw the trend that those vectors follow. Okay, so that's what we want to draw, or be able to draw, right here. All right, the fact that close to the charge, the field lines point away, but then they start to be affected by the other ones. Right here, we'll draw down like this, and then bend away. Here we'll draw away from the charge, but bend away. Away from the charge and bend away, and so forth. Here it just goes straight away, because it's straight away from both of them. Right? So we have a field that looks like that. The only thing that would change if these charges were negative is the direction of the lines. The lines would point toward the charge. All right? Now, for 2 opposite charges, let's call it a dipole field. Di, 2, poles, 2 different charges. Close and clear, yes. So reset. Let's do this. I'll do a -4 and a positive 4. We get a very classic field that has this shape like a football or a spider or something like that. All right, called the dipole field. Okay, and again, we got to be sure about the fact that, say, right here, leave me alone. Sure, right there, here's a negative charge right here, negative charge, right? So field due to that one points this way. Okay, here's a positive charge. Field due to that one points this way. They're the same charge. We're the same distance from each. And so the total field at that point is the sum of those two electric field vectors, a field that looks like that. And notice that's tangent to the curve, tangent to the field line at that location, points to the left. All right, so those are little things you ought to be able to do. A, identify the fact that field lines point tangent, well, the actual electric field points tangent to the field line, and you ought to be able to do those little simple vector operations to figure out general direction of electric field. Okay, so if we go back to our slide here, dipole field, what's that all about? Sure, dipole field looks something like this. In this case, we have positive on the left, so we go away from positive, negative on the right toward negative. We go like that. Away from positive, it bends toward negative. Away from positive, bends toward negative. So, whoops. So that's, see the asymmetry there? Not good. We want to have it nice and symmetrical. We'll bring this out, assume that it comes back. Bring that one out, assume that it comes back. Remember, we said electric field lines don't end. Well, I guess they end on the charge here, right? But the electric field itself extends infinitely far away from these charges. Okay, good looking dipole field there. Now, the deal with this, with our charges of different magnitudes, well, as you might be able to guess, reset, I'll do a positive 1 and a negative 5. Yeah, that shows kind of what we want to show. First of all, hopefully you can notice that, how do you tell if a charge is weak or strong? Or how do you tell if a field is weak or strong? Well, by the number of lines, right? And the smaller a charge is, the smaller the field it makes, so the fewer lines come off the charge. The greater a charge is, the stronger the field it makes, the more field lines we represent that by. So you notice here on the left, we have lots of lines touching the blue negative charge. On the right, we have a lot fewer lines touching the smaller positive charge. All right, and literally, if you do it right, if you count these up, there's a ratio of the lines that touch this one and the lines that touch this one. That ratio is the same as the ratio of their charges. Okay, so if we go back here, all we really have to be sure of is that we draw, again, this will be away from positive toward negative, away from positive. Now this is going to, notice here I do have the asymmetry, because the farther and farther you get away from this stronger positive charge, the more it seems like that's the only charge in town. It's not till you get close to the negative that charge or that field really takes over. So I'll draw lots of lines coming off this positive charge, but a relatively small number of them touching the negative charge. And I should, this is a real stickler thing, but we do want to make sure that field lines actually touch the charge. I think AP will zing you on that if you don't draw them all the way there. I think the Regents will at least. Okay. Okay. Now this hollow conductor, the applet has a hard time with this. All right, because for a couple of reasons. One, we can't actually make enclosed shapes. All right. What we can do, the best we can, is to try to just put like, oh, those are maybe too strong. Let's go down to 1s. We'll try to put a bunch of them in that circle. You can only put so many. It's like 22 before the applet starts taking old ones off as you put new ones down. Might be happening right now. But as it draws, it's a real mess, right? And it's making some calculational errors just because we're asking it to make a lot of calculations. And here for sure are some calculation errors. Field lines never cross. That would say that a charge would feel two different forces or forces in two different directions. That doesn't happen. You know, if you sort of use your intuition hat a little bit and say, well, generally what's the field like? You know, blur your eyes a little bit. Well, gee, it kind of looks like the field just made by a point charge, right? At least outside the ring, those are lines that just point, in this case, point toward, because it's a negative charge. They point toward some central location, right? And so that's the deal with what we call hollow conductors, especially round ones. All right, so we're going to say that since these are positive charges, what we get is a field outside the ring that looks just like the field made by a point charge. Field lines are always perpendicular to the surface. Right, that works for any field or any surface of charge. Field lines are always perpendicular to the surface. But the big deal is this. Inside, there's zero electric field. All right? There's no electric field inside a hollow conductor. All right? Big deal there. There's some symmetry reasons for that. There are derivations, some simpler than others, that you can do to show that, but that's a big deal for us. Inside a hollow conductor, zero electric field. No electric field at all. Okay? Now, this is a really common charge distribution we need to deal with, and it refers to what we call parallel plates. All right? Now, one big assumption here is we assume that the plates are infinitely long, or we'll just say really long, or maybe we can assume that the separation between the plates is really small compared to the length of the plates. All right? That allows us to neglect things that happen towards the edges, which we don't really want to deal with. All right? And the applet does not a bad job of this. So if I reset, oops. Yep. If I reset, and I'm going to put, well, I'm just going to put one line of charge. This does a pretty good job. Yeah, this is great. Now you notice both above and below, and especially towards the middle, right? Say here and here. Forget about the ends. You know, what do you notice about, say, here and here and here? Well, hopefully you notice that the lines are evenly spaced. All right? Notice that starts to change over here where there's curving going on, but these are evenly spaced and parallel. Right? We can tell, looking at a point charge, where the field gets weak because the lines spread out. These lines don't spread out. That means the field doesn't change strength. All right? That's a big deal, a really big deal. All right? If we go back here, if we say that, well, inside here, the field made by these positive charges would point away from the positive. Nice and straight, nice and parallel. Now at the end you actually get some curving, fringing I think they call it. Now that would actually also happen out here. We'll get this, and this, and this. And it would also continue out here, hypothetically at least. Hold on to that thought for a minute. Oops, I'm changing my spacing. Forget about that. Now, from the red negative plate, well, field points toward negative charge. So I'm going to say that inside the plates, we'd have field like this. Now, out here to the right, again, field points toward negative charge. We get a field like this. Outside over here to the left, field points toward negative charge. Now I hear what you're saying. You're saying, yeah, but you're farther away from that plate, so, you know, or closer or farther from the plate, so aren't those fields, you know, different on the outside? Well, they're not, because we assume that the plates are really, really long, and therefore these field lines really never get closer together or farther apart. The field is pretty constant. So literally out here on the right, we get a field one way from the positive charge, a field the opposite way from the opposite charge, that means that out here, E is 0. Same thing on the left. We get a field to the left from the positive charge, a field to the right from the negative charge. That means that out here, E is 0. Okay, but inside, we get what's called a uniform electric field. Uniform meaning constant. Notice, the lines are evenly spaced and parallel. All right, they always point in the same direction. They're always the same distance apart. That means the field has a constant strength. All right, just like the gravitational field in this room. From floor to ceiling, the field is so close to uniform, so close to exactly the same strength and direction that we never even worry about the difference. We just say the field is such that it gives things acceleration of 9.8 meters per second per second. All right, this is an electric field that models that kind of gravitational field. All right, so a few questions. One, what's the direction of force exerted on an electron? Well, two ways to think about that. One is, what direction the fields point? Well, they point in the direction of force that a positive charge would feel. So a positive charge apparently would be pushed to the right because this field points to the right. Therefore, a negative charge would be pushed in the opposite direction. Well, of course, also, if you look at the charges on the plates, you put an electron in the middle, it's repelled by the negatives, it's attracted by the positives. That means it's pushed to the left. All right? Well, the proton's the opposite charge. Of course, that's going to go to the right. Trick question. There's three choices, A, B, and C. Where does a proton feel the greatest force? Think about it. Pause if you must. Answer. Nowhere. Force at A equals force at B equals force at C. It's like saying, where does a 1 kilogram mass weigh the most? At the ceiling, at eye level, or at the floor? It weighs the same everywhere because the field is the exact same strength. Fields exert forces. If the field's the same strength, the force is exactly the same. Okay? Now, let's do this. For the last one, we have an electron that we put in the field. What's its acceleration? Well, we said that it would have a force on it, Fe, this way. Right? With that, we write a simple net force statement. And that says that Fe equals mass of an electron times its acceleration. Well, the force exerted by the field on the charge is charge times E. I'm going to rewrite that Q as E for elementary charge times the strength of the electric field divided by the mass of an electron. That's how fast it accelerates. Okay, so we can mix. The nice thing is we still use Newton's second law for lots of stuff, even in this unit. Okay? Now, here's a little connection, again, between gravitational stuff and electric field stuff. Okay? So mass in a gravitational field, we give it a velocity this way. All right, what does it do? Sure, it acts like a projectile. I mean, it is a projectile. Right? It does that. It covers some horizontal distance, delta x. Right? It falls some distance, delta y. And we can do things like say, well, since this has an initial vertical velocity of 0, we can say delta y is v naught yt, nothing, plus 1/2 gt squared. Right? And the time it takes to cover some distance, delta y, is 2 delta y over g. Should look familiar. All right? How far does it go before it, hits the ground, say, if we assume, here's the ground. Well, how far does it go? It goes some distance, delta x, where we say that's vx times t. If you want, plug this stuff in for t. Right? Let's do a different one where we talk about an electron in an electric field. All right? And let's make it so that this thing doesn't fall downward like a mass always does, but that it goes upward as a projectile sort of thing like that, right? Or at least that it follows a parabolic path just like a mass in a constant gravitational field does. Well, how can we make it do that? How do we make it so that there's a force on it, Fe, like that, that's analogous to the force on this thing, Fg? Well, again, if we want a charge to be pushed upward, this is a negative charge, that means that the field must point downward, right? Fields point in the direction of the force that a positive charge would feel. This is a negative charge. Right, so field looks like that, which means this is positive plate, this is negative plate, nice brown color. You know, and how do we, what's our analogy here? Well, we could still say, if we use our same coordinate system, we can still say that V naught y is 0. We can still say that delta y is 1/2 at squared. Well, what's this thing's acceleration? Remember from the last slide, right? We said here's acceleration. Sorry, here's the electron. There's a force on it like this. Well, Fe equals ma, or charge on an electron times the electric field strength equals mass of the electron times a. Or again, A equals, again, I'll rewrite QE as just elementary charge lowercase e, like that. So we put this stuff in here. And we can say, okay, delta y is 1/2 e t squared over mass of an electron. Or the time it takes to get to the other plate to cover that distance, if we call this as our delta y, well, t is, let's see, 2 delta y me over e. Right? That's a subscript e right here, subscript. And, of course, square root. Right? And how far does it travel? What distance? Delta x? Well, again, delta x is just Vx times t. Or we call this the Vx. All right, so these are the exact same thing, but you know the question is, what's acceleration? Here it's just g. Right here, acceleration is different because it deals with the effect of the electric field. All right, that's a lot. Oh, I'm sorry, one more thing. What's the strength? Oh, yeah, okay. So this last little question here. What's the strength and direction of the field such that the electron's path is undeflected? Now, the one thing that we did up here is this is neglecting, I should have mentioned this, neglecting gravity. All right, now, we know hopefully by now that electrostatic forces are way, way, way stronger than gravitational forces. Sort of pound for pound, that's not the right way to say it, but here if we don't neglect gravity, we can say as this thing moves through the field, well, for sure, there's a gravitational field, sorry, a gravitational force, Fg, that acts on that electron. We want its path to be undeflected. That means that there's going to be an electrostatic force that points upward. Now, direction we'll get to in a minute, but if these two, if this path is undeflected, well, then we say these two forces are equal. Or we can write the strength of the electric force as Q times E. I'm going to stop writing it as Q. Since this is an electron, I'll write it as charge as lowercase e. And this is mass of the electron times G. Well, what's the strength of the field? There it is. Doesn't matter how fast it's going. As long as you have an electric field that's that strength, sorry, that's this strength, an electron can go straight through this set up here without being deflected at all. Now, if we include gravity up here, the expression gets a little crazier because it's, this changes. Our net force statement isn't just Fe. It would be Fe minus mg. So it's kind of simpler it's nice to be able to neglect it there. Here we don't in the bottom. Now, direction, like we said before, right? If we want a force upward on a negative charge, we need an electric field downward. All right, electric fields point in the direction of the force that a positive charge would feel. This force points up. On a negative charge, the field must point downward. Okay, a whole bunch there, but this will equip us very well for what's coming. Okay, thanks, folks.